Okay, so I think it's time for us to start thinking about general orbits and orbital mechanics. So we've been playing around with stuff moving near the surface of the Earth quite a bit. We've even included a few things like drag or thrust, etc. But it's time to go beyond. This is the Kepler problem. In other words, how do things like planets and satellites and stars, etc., move about in the influence of general Newtonian gravity, not just mg close to the surface of Earth, so non-uniform gravity. And of course, this is a very important subject from the history of science perspective. This is what made Newton, well, super famous, or at least he kind of invented a lot of his work on dynamics and the calculus to solve this particular problem. For millennia, astronomers had tracked the motions of the planets, the moons, the stars, etc., across the night sky. There were data tables going back hundreds and hundreds of years, and patterns had emerged that were very difficult to explain. Newton then took those patterns and came up with his general idea of universal gravitation as being an inverse square law. We're going to go in the opposite direction and take it as a given that the inverse square law applies for Newtonian gravity, and from that predict the orbits that Kepler had postulated were conic sections. So kind of going in reverse, which is actually the easier way around. So Newton was definitely a genius. Weird guy, but a genius. Okay, so here's the situation. We're going to break this into a couple different videos. So first off, I'm going to call this Kepler 1, which means we're going to start from very general considerations and work our way towards the specifics of the inverse square law. The first thing we want to look at are what are called central forces. Imagine I have two objects. Let's call them mass 1 and mass 2. And these two objects exert forces on each other. Never mind what kind of force right now. Maybe it's gravity, but it could also be some sort of elastic force, or maybe some sort of, who knows, weird electrical force or magnetic force. We don't really know right now, but they exert forces, and we're going to make a very particular assumption. We're going to assume that these two forces act centrally, which means they're each pulling on each other along the line of sight between them. So in the drawing here, this F21 is the force on object 2 due to object 1, and this F12 is the force on object 1 due to object 2. By Newton's third law, these should be opposite vectors, but the important thing here is that they're along the line connecting these. And that's not true for all forces. For example, magnetic forces don't actually do this. But if this is true, and these are conservative forces, which means they're derivable from a potential energy, then the general potential energy, which could arbitrarily depend on the locations of the two masses in some generic sense. So notice I put a little coordinate system here, which is an arbitrary origin. It does not have to be Cartesian coordinates. It does not have to be at the center of mass. It's just some arbitrary point in space. Vector R1 and vector R2 are the vector positions of these two masses. And in principle, the potential energy of the system could just depend on those two locations quite generically. But by forcing this to be a central force, it means that this general expression for the potential energy is actually only a function of the magnitude of the distance between the two. Let's call the magnitude of that distance R. And in fact, we'll define the vector R. I'm going to define it actually as R1 minus R2. So in this setup, it would actually be something like, let's see, don't have a lot of room here, but it'd be something like this vector right here would be vector R. It's the difference between the two green vector locations. What I really care about, though, is its magnitude. And its magnitude is just going to be R with no vector sign over it. And notice that that will not depend on my origin, which is good. It means I can choose my origin arbitrarily. In fact, one of the first things we'll do is try to pick a nice origin for working in these settings. While I'm at it, I'm going to write down a couple other things that we'll see will be useful. This capital R vector, notice it's kind of like a sum of the two R1s, except they're weighted by their mass. So it's the mass of object 1 times its position, plus the mass of object 2 times its position. And notice that the numerator right there would be, well, something like the first moment of mass, if you want to put some term to it. When I divide by the total mass, m1 plus m2, this really is the position of the center of mass. So this weighted position of these two locations by their mass will be somewhere on the line between them, and that position is called the center of mass. We'll also introduce a couple other terms. So this capital M, I'll just call that m1 plus 2. It's the total mass of the system, so the total mass. And then this mu is the product divided by the sum, or said another way, the reciprocal of mu is the sum of the reciprocals of the masses, so their harmonic sum. And this is called the reduced mass. So if you want some terminology here, we could say that this thing is the reduced mass. This thing is the total mass. And this thing is the center of mass. Sometimes that's called the CM. Okay, so what do we want to do? There's a few things we want to do now. First off, I want to show that this generic sort of two-body interaction, I've got two objects, can be reduced to a single effective object, and that's going to make my analysis way easier. So the two-body problem is completely solvable in Newtonian mechanics, because I can reduce a two-body problem, at least if it's a central force problem, I can reduce it down to an effective single-body problem. Then we're going to prove a couple interesting results, like we'll prove that the motion has to lie in a plane, we'll prove that angular momentum is conserved, and we'll prove Kepler's second law about areas. Okay, so let's start by showing that this two-body interaction really does reduce down to a one-body effective interaction. So I'm going to start doing this by rewriting my center of mass coordinate. And now I want to take the second derivative of this. I will invoke Newton's third law to make this vanish. So you might say, well, are we allowed to use the third law? The third law is equivalent to conservation of momentum, which we haven't really shown here, but it is one of the base laws of Newton, so I'm going to invoke it here. And it will basically let us say that the net force on this system is 0. So let's take the second derivative. I'll indicate that by using Newton's notation in honor of the man. So these are the double dot notation, means the second time derivative. Notice all the masses are assumed to be constant here. Okay, now mass 1 times the acceleration of position 1, or object 1, well, that's just the force on object 1. And there's only one force acting on object 1, it's F12. We're assuming this is an isolated system, so there are no external forces. It's just the two forces, 1 on 2 and 2 on 1. Similarly, MA for object 2 will just be the total force on object 2, but there's only one force acting on object 2. It's the force on 2 due to 1, which maybe it's gravity, but right now it's just some generic central force. But look, by Newton's third law, these are equal and opposite vectors, so I just get the 0 vector. In other words, the acceleration of the center of mass is 0. The center of mass provides a nice inertial frame where I can measure all of my relative positions to the center of mass. So instead of picking this arbitrary location for my coordinate system, it'll be way more convenient if I just choose my origin to be at the center of mass. So let's go ahead and modify this diagram so that we choose that, because I know that the center of mass is not accelerating. Okay, so now look over here. We have this x will represent the center of mass. I'll call that the CM. Eventually, I'm going to choose to capital R, to be the vector 0, because it is supposed to be my origin. But for now, we'll leave it in as perhaps something you might want to choose. But the important part is that the center of mass does not accelerate. These two objects can move around about the center of mass, but the center of mass provides an inertial frame. R1 is still measuring the location of mass 1, now with respect to the CM, and R2 is measuring the location of mass 2, again with respect to the CM. We still have these two equal and opposite forces. We can also invert this equation, combining it with this relative position vector to solve for the positions of mass 1 and mass 2 in this system in terms of the location of the center of mass, which again could be 0, and the relative vector separation. And remember, we've defined that as R1 minus R2. So it's just a little bit of algebra to go solve for these R1s and R2s, a system of 2 equations. And you can check that if you do take this R1 and this R2 and plug them back in here, you'll get capital R, and if you plug them back in here, you'll get little r. Remember, this capital M is the total mass. Okay, what we want to do now is we want to see how this has sort of effectively been reduced to a single object in a way. Okay, and to make this work, we're going to invoke the Newton's second law, basically, for each of the 2 masses, one by one. So for mass 1, I can say that its mass times acceleration, the second derivative of its position, is going to be some magnitude. So this F of r is a magnitude of the force. It is a central force that only depends on the relative separation of the 2 particles. And we need to give a direction based on the way we've drawn this, since r kind of points from object 2 to object 1. And I want, for now, we're kind of thinking of attractive forces, although, of course, this could be repulsive. It doesn't really matter. I could imagine writing this as negative f of r times this unit vector that points in this direction. So r hat would be the unit vector from 2 to 1. F1, 2, I've sort of decided this is an attractive force, although it didn't have to be. And that's why this has a minus sign. There's absolutely no reason why I couldn't have just replaced this with a positive sign with 2 sort of pushing away from each other forces. That's fine. We can do the same thing for mass 2. Notice it only has one force acting on it. It's the same magnitude force, but of course, the way I've drawn it, that's going to be attractive. And now, if I subtract these 2 equations after moving the m's over, I'll end up with something like R1 minus R2 double dot. Okay, so let's make sure we understand that. So I took this, I divided by m1. I took this, I divided by m2. I subtracted them from each other, so I actually pick up a minus on both of the terms. And this is equal to r double dot. Let's now invoke this idea of the reduced mass, because 1 over m1 plus 1 over m2, I can factor the negative f out of both terms, is 1 over mu. So this is negative f of r over mu times r hat. And then multiplying the mu over, we end up with this second order differential equation, but it looks a lot like Newton's second law. It's just that now we have a single object, which is at location r. Notice that's not really any of these objects here, but there's a sort of position, which we'll call this vector r. The second derivative of it times this mass, which again is not a mass in the problem, but it's made out of masses in the problem, equals some kind of force. The negative sign is just because I was kind of choosing attractive, but of course it could be repulsive too. And it's a central force. It points along the direction to this imaginary mass. So this right here is really telling us that this is a one-dimensional problem now. I can treat this two-body problem, which would have been R1s and R2s both circling the center of mass, with this single effective separation. So the whole problem has reduced down to an effective one-body problem, the motion of a single reduced mass at a position R, which is this sort of relative separation between the 2 original masses in the problem. And a one-body problem is much easier to solve because I only have one sort of position to keep track of. Oftentimes, we'll be looking at situations where one of the masses is so much bigger than the other that the center of mass is practically at the location of the heavier mass. And then this really does sort of model the orbit or motion of a single light object around a heavy second object. Okay, so this is one way of getting this. Let me show you one other alternative derivation involving energy conservation. Okay, so here we have an expression for the total kinetic energy of the system. And I want to show that by using these two results we've gotten earlier, we can again see another way that the system is behaving like sort of a single mass that's moving about the center of mass. So I'm just going to sub these two in and we'll see what happens. Okay, got a little long there, but we fit it. I took the derivative of each of these, and of course the masses are constant. And now I just need to square these, meaning take the dot products with themselves. In the first bit, notice I'm going to get an r dot squared. There'll be a dot product between these two velocities, and there'll be a factor of 2. And then there'll be a square of this term. Okay, that's the first one. I'll write the second one below that. This time there'll be a minus sign here, pretty important. Whew, okay, starting to bleed down a little bit there, but we're okay. And now I want to simplify. What happens? Well, let's take a look. This middle term here with the 1/2 times m1 times 2m2 over capital M r dot r dot, r dot dot r dot, and this minus sign in the second term with the m1 and m2 swapped, but it's still the same product, cancel. So this term and this term cancel each other. That's kind of nice. The m1 plus the m2 out here, I'll just group that into a capital M, because that's the total mass of the system. So this first term is basically the kinetic energy of the center of mass. It's the motion of the center of mass as a whole, the total mass of the system, and where is this center of mass moving through space. So that's been kind of decoupled. What's left, if we're careful, is a 1/2, okay, so there's going to be a 1/2, m1 m2 squared over big M squared plus m2 m1 squared over big M squared. Let's write that out. m1 m2 squared plus m2 m1 squared all over big M squared, and then we have this relative velocity squared. But look, we can simplify this a little bit. We can see that I can factor out an m1 from both of these, and I can factor out an m2 from both of these. And when I do that, I'm left with an m1 m2 times m1 plus m2, but that's just big M. So I can cancel that with one of the powers downstairs. But what does that leave? It's m1 times m2 over m1 plus m2, which is exactly the definition of the reduced mass. So at the end of the day, the two terms are a center of mass kinetic energy plus a relative motion kinetic energy. So the kinetic energy of the center of mass moving through space, and then the kinetic energy of the relative motion about the center of mass. And again, we kind of see that the two types of dynamics have decoupled. The center of mass itself is not accelerating and is just sort of flying through space, perhaps, although usually it's easiest to just sort of set that equal to 0 and only look at relative motion. And then this r dot is the relative kinetic energy term. Again, we've seen that we've effectively reduced this to a one-body problem. Okay, so that's it for today. Next time, we'll come back and look at a few more generic cases of what might be conserved or general results for central forces. QED.